Hello everyone, welcome to the next lecture in the topic remote sensing with imaging radar. So, in the last lecture we discussed briefly about the radar equation, what all the different factors that will control or that will influence the radar backscattering coefficient, and we started discussing about surface roughness. Today we will continue exploring the other factors that will influence radar backscattering coefficient. So, the next important property other than surface roughness that will influence backscattering coefficient is the moisture content of the surface. Like when we discussed about passive microwave radiometry, I told you that addition of water to the soil, like let us take bare soil as an example. Addition of water to bare soil will increase its conductance, thereby increasing its reflectance and lowering its emissivity. So, wet soil surfaces will have lower brightness temperatures. We have seen this is in passive microwave. There I told you that adding water to the soil will increase its reflectance. There reflectance I meant backscattering. Okay. So, the backscattering of the soil or whatever feature on the earth surface, whether it is vegetation, will increase with increasing moisture content. So, higher the moisture content of the surface, higher will be its backscattering coefficient. Also what the water will make how the water will behave is like it will also reduce the penetration capacity of the microwave signals. Again the similar concept I have explained during passive microwave classes, that microwave signals has the capacity to penetrate to some extent in different objects, be it vegetation, be it like bare soil, etc. So, the depth of penetration will reduce as the moisture content of the surface increases. The penetration will be lower for wet surface. Okay, why this penetration is important? Penetration will change the way how microwave interacts with the objects. Let us say not only microwave, let us say any particular electromagnetic radiation, if it interacts only with the surface feature, like just the surface of the object in the terrain, most likely it will act as kind of like a what we call it as kind of surface scattering or surface reflection. Most likely the polarization of the wave that is incident upon will be preserved, may not change. Whereas if the signals penetrate through the object of interest, there are high chances that the signal will interact with different discontinuities within the object, may get reflected multiple times, leading to a more diffuse kind of scattering in which the polarization of the signal may change, that is the signal may get depolarized. That is, let us say like what is given here is an example for like volume scattering. Let us say some electromagnetic radiation is penetrating into the object. So, these are all maybe molecules or whatever feature present within an object, it has lot of air gaps and everything. Because of this discontinuity, we call it as like discontinuity, when there is like a change in medium within the same object itself. Like when I discussed about the leaf reflectance, especially in NIR band, what I told you, like a single leaf may have cells within it with lot of air gaps between them. So, this forms like an discontinuity, like in the infrared radiation will travel through the cell, may get reflected again at this discontinuity medium, right. Same thing may happen with microwave wavelength also. Each of this discontinuity may produce multiple scattering, leading to an overall volume scattering in which the wave can be depolarized. Okay, that is, let us say horizontal polarization was incident upon the surface. If it is like a pure surface reflection, like the microwave has not penetrated through the object, most likely a large fraction of energy may still be horizontally polarized, that is reflected back from the object. On the other hand, if the electromagnetic radiation penetrates through the object and interacts with large fraction of the objects, large fraction of the discontinuity is present within object, most likely it may become depolarized and the large fraction of energy that is being backscattered by the object may now be in vertical polarization. This can happen. So, the penetration of microwave has the capacity to or the penetration may change the polarization of the incident signal. So, with this general background like how surface roughness interacts with microwave, how moisture content interacts with microwave, how penetration changes the polarization. With this general background, we will briefly see the general characteristics of interaction of microwave signals with different features on the earth surface. So, the first thing is vegetation, how microwave signals will interact with vegetation, or what are the factors of vegetation that will influence this backscattering coefficient. So, some of the important factors of vegetation are the biomass content, like how dense, whether like it is like a dense vegetation or it is like a sparse vegetation, the total biomass content, the plant height, like whether it is like a woody or non-woody tree. Woody means like large trees with huge trees with large stems and barks and everything, or like a non-woody vegetation. Non-woody means like grasslands. These things will influence the backscattering coefficient. The canopy structure, whether it is like a needle like structure, whether it is like a broad leaf like structure, how rough the total canopy structure is. Like a well maintained grassland may appear like perfectly smooth if you look at it at some angles, right, but a forest canopy may appear like totally rough to our eyes. So, both of them are vegetation, grassland and forest canopy, but they may have different surface roughness. Like if the grass is like perfectly laid out on the surface and it is cut exactly to like one particular height, it may appear perfectly smooth, but an area covered with large trees may appear kind of like a really rough surface with rugged canopic nature. So, this overall like geometry of the canopy, water content within the canopy, whether the vegetation is dry or not, all these factors will influence the backscattering coefficient from the vegetation. And here we also have to remember that unlike optical remote sensing, where the signals, either a reflection or emission, will be happening only from the top millimeters of the surface most likely. In case of microwave, the signals that has been backscattered will not only be from the canopy part or the leafy part, may also happen from the stems, branches, leaves, even the soil underneath the canopy cover. It can happen depending upon the wavelength involved, canopy water content and so on. So, the signals that we may get in radar images may not only give us information about the leaves, but also about like the various features present underneath the canopy. Okay. This thing we always have to keep in mind while we use radar images for applications related to vegetation monitoring. So, this is like a very schematic or like a highly simplified explanation of or radar interaction with vegetation. So, any incoming signal may just get reflected by the surface, that is undergo surface scattering from the top of the canopy, it may go back. Some fraction of the incident radiation may penetrate into the canopy and can interact with the stems, branches, leaves and something else that is present underneath the canopy and all these things. So, this is what we call it as volume scattering, like scattering happening underneath the canopy, but still everything is confined within this vegetation. So, this is like a dense network of trees. So, everything is still happening with under the domain of vegetation alone. So, here we call it as volume scattering. A further fraction of the incoming signal may still reach the surface, may undergo surface reflection or even may penetrate under the surface, may undergo volume scattering by like the soil elements under the surface and can still come out. Surface and volume scattering from the ground. So, essentially the instant signal can take these multiple paths: surface scattering from the top of the canopy, volume scattering within the vegetation volume, or surface and volume scattering from the ground. So, essentially not only the vegetation properties, but also the surface properties, whether the surface is dry or wet and so on, will have like a combined effect in the backscattering coefficient that got recorded in the radar image. So, just to drive this point further, we will look at like a highly simplified model of microwave interaction with the vegetation. We will first take an example of woody vegetation like a forested trees, large chunk of large trees with huge branches, stems, barks and everything. So, the incident signal, the microwave signal will get backscattered from the canopy, like this is like a surface scattering from the canopy, or some of it may penetrate, interact with this woody part like the trunk part and may be reflected back. So, this is the backscattering from the woody portion, the trunk portion. A certain fraction of the incident radiation may have higher penetration and can reach the surface and can directly escape this canopy part. So, this is like the reflection coming from the surface, backscattering from the surface. A certain fraction of it might have reached the surface, get forward reflected, interact with this trunk and may come out. So, this is what we call it as kind of like a double bounce. Like a significant good fraction of the incoming incident radiation may be reflected in the forward direction and kind of like a vegetation trunk may be standing in front of it, which may reflect it towards the sensor, a double bounce, or there can be multiple reflected signal, like here it is like simplifiedly given as one way, but the same radiation, same wave of the radiation can undergo multiple reflection within this canopy itself and may finally escape. So, the net resultant backscattering coefficient that got recorded depends on the surface scattering from the canopy, the surface scattering from this trunk and the surface, the double bounce effect and the mixed or like the multiply reflected microwave signals. So, apart from these things, apart from only this surface scattering from the canopy, for all other components that is happening below the canopy must pass through the canopy once. So, the canopy's transmission or the transmissivity of the canopy comes into picture. Okay, so, here we have put a square because it has to first travel inwards crossing the canopy, then the backscattered signal should also travel outwards again crossing the same canopy. So, that is why we have this square term. Similarly, the trunk also has some sort of penetration cover, okay, capacity. So, as like a in like a simplified manner, if you want to think of the net resultant energy that is reaching the radar antenna depends upon not only the canopy characteristics, but also the surface characteristics, the trunk, how the geometry is aligned. Let us say like the canopy is not very dense, then like a high fraction of energy will reach the soil, will interact with whatever is present in the soil and can come back and all these things. Okay. And also imagine, let us say like a good fraction of energy is going towards the surface, and let us say that the surface soil has good amount of moisture content, then what will happen? It may produce like a bright backscattering coefficient towards the radar. So, that surface scattering component can be really stronger. On the other hand, let us say there is like a standing water present, like maybe like a wetland or like a rice paddy field where the paddy crop is just emanating from the standing water column. When that happens, what will happen? This is like a standing water, here there is like vegetation standing over the water column. Let us say some microwave radiation is incident upon it. Here also there is vegetation, but some radiation has penetrated into it. What will happen? Since this is like a standing water column, this will specularly reflect, a large fraction will move towards this vegetation. And since this has like, if we think it as like a healthy vegetation, then it will have high backscattering coefficient and it will reflect a strong signal towards the radar antenna. So, this kind of double bounce has the capacity to produce a really bright backscattering effect. Okay. So, it depends on how much microwave that penetrates through the canopy. If the microwave is not able to penetrate the canopy, like canopy has very high amount of water content and we are sensing in very shorter wavelengths, say X band or something, then the penetration capacity will get lower, signal may not even reach the surface. So, based on the sensor characteristics and the object characteristics, the backscattering received by the radar from vegetation will be having like a complex signal embedded within it. Again, just to drive home the point of radar penetration depth and frequency, we are going to like see some schematic examples. Let us say like there is like a vegetation canopy, identical vegetation canopy. If we irradiate it with, or if we observe it in 3 different bands, X band radar, C band radar and L band radar, most likely the shorter wavelengths will contain information only about the canopy part, that is the top surface of the canopy. Whereas a C band may have little bit higher penetration, may provide some information about the entire canopy depth and also something about this woody part or something. If we look at it kind of like a much longer L band radar, then it may even contain signal about the soil that is present underneath it. So, by changing the observation frequency or the observation wavelength, we may get information about different components of vegetation, whether just the leaves or like the entire leaves plus woody part or even like the underneath soil. So, longer the wavelength, more will be the penetration, that is one thing. And also like depending on the moisture content. So, higher the moisture content, lower will be the penetration. This also we have to remember in mind. Okay. Higher moisture content, lower penetration. Also what we have to remember is, like I told you, like longer wavelengths may penetrate deep into the canopy and all. So, and also like radar may have the capacity to produce images in multiple polarizations, HH, HV and so on. So, most likely the cross polarized images like the HV image or VH image may contain information about the underneath the canopy part, like the volume scattered part, like the trunks, stems, branches and so on, whereas the light polarized image may contain information about the top surface canopy part because of this surface scattering and volume scattering. Volume scattering most likely may tend to depolarize the signal. If it is horizontally incoming, the outgoing may be vertical and so on. So, this depolarization may occur as a result of this volume scattering. So, using multiple polarized radar images, or even we may not use different frequencies, but even within a given frequency, looking at images having different polarizations may give us different information about the vegetation. So, this slide gives kind of like a example for a radar image. So, this is like a Amazon rainforest, a portion of Amazon rainforest that is imaged through radar. This is like an X band radar, VV polarization, C band radar HV, L band radar HV. So, these two are cross polarized, this is like a like polarized. Okay. This is like a rain bearing cloud containing good amount of water. So, in X band radar, which is like around roughly 3 centimeter in wavelength, the cloud is clearly visible, that is the radar is not able to penetrate through the cloud because of like it is like rain bearing. So, it may be raining also during the time of image acquisition. So, due to which we are not able to see what is present below the cloud. In C band, the cloud is present, but still we are able to see some portion of the land surface, whereas in L band the cloud is almost absent. We are clearly seeing the ground surface without any interference from the cloud. So, this tells us longer wavelengths are useful for all weather monitoring. This is one information we get from this analysis. Second thing, this is like a river. So, this river channel, since it is like a water is present and water acts as a specular reflector in microwave wavelengths. In all the images, river channels appears much darker. So, any water bodies present in microwave images may appear darker. This is another thing that we may get from this particular images. Then one more thing that you can observe is, like, take a look at or compare this X-band C-band image, like these patches especially. Here we are seeing or we are able to see like alternative dark patch and a bright patch. So, here there is again like a very bright patch and dark patch. In C band also it is present, but to some extent. In X band also it is present to some extent. What these are? In L band image, these bright patches represents forest, whereas this dark patches represent cleared forest, that is deforested land. So, this is like a bare soil surface here. So, these are deforested lands. So, what essentially happens in X band radar and L band radar is, in X band radar, say this is like soil, this is like the tree. So, this is like cleared deforested area, this is like a still forested area, not vegetation is still present. Both of them will have some sort of surface roughness, right. This top of the canopy and also the soil. So, here in X band being like a shorter wavelength, even the bare soil appeared rough to the radar and it produced good amount of or relatively higher backscattering coefficient in comparison to the forest surface. Whereas in L band radar, the bare soil surface, the surface roughness is not, actually the bare soil surface appears smooth and hence it is appearing dark in L band signals, whereas forest surface, due to the presence of healthy vegetation with high water content and good surface roughness, it is appearing bright in all the images. So, the same area, but imaged in different frequencies gives like a different view of the land surface, and we may get different or complementary information out of these images. And also if we have a look at the images again, you can see like the L band images is like kind of cross polarized, HV polarized image. So, it may contain not only the information about the canopy, but also information about the volume scattering elements present below the canopy. So, this slide tells us again, like reinforces the effect of water on the radar image. So, as I already told you, water bodies may appear like completely dark in radar images because of the highly specular reflection nature of the water bodies, and presence of vegetation over standing water may result in double bounce, leading to a very bright signal received in the or stored in the radar image. And urban response. So, normally like urban structures, the orientation of urban structures like buildings or whatever features on the urban cities, if they are present in a direction orthogonal to radar signals, they may produce what is known as a cardinal effect. Say this is like a Los Angeles County in the United States. So, this is like two cities, San Fernando and this is like Santa Monica, and these are again like the entire Los Angeles, which is highly urbanized portion in the world. Here this is also urban area appearing darker, this is also an urban area but appears much brighter. This is because if the orientation of the urban features, if they are oriented in a direction perpendicular to the incoming radar signal, they may produce bright backscattering, that is known as the cardinal effect. Okay. So, this is again one more example for radar interaction and the geometrical nature of objects, how it will change the radar backscattering coefficient. So, the another major advantage of using like satellite based radar remote sensing is, the recent radar remote sensing satellites has the capacity to image the ground in different modes. So, what are the different modes means, like we know each imaging system has certain characteristics like swath width, spatial resolution and so on, right. So, a radar can change its characteristics, or we can tune the radar image acquisition based on our needs. Say for certain application we may have to increase our swath width for covering a larger area, that may be possible. Or for some applications we may be required to get very fine spatial resolution images, possible. We can configure the radar antenna even after it is launched. So, nowadays the recent radar remote sensing satellites has this multiple imaging capabilities or multiple imaging modes for getting images based on our needs. Say an example is given with respect to a radar satellite, which is like a commercial satellite where we have to pay and get the images. So, here you can see that it has lot of different modes of image acquisition, like it can produce very fine spatial resolution image sacrificing the swath width, or it may produce a large image over like a large area covering like a very wide swath sacrificing the spatial resolution, or we can even increase the spatial resolution decreasing its polarization capacity, like we can reduce the number of polarization modes rather than collecting images in HH, HV, VV and BH in all the 4 polarization, we can reduce some of them for spatial resolution and so on. So, in radar remote sensing the satellites are now has the capacity of multiple imaging modes in which we can obtain images based on our needs. So, normally this feature is not widely seen in optical remote sensing satellites. So, once a satellite is launched, swath width, spatial resolution, everything is fixed. The only advantage what we can have is we can tilt the cameras. Some of the optical remote sensing satellites has the capacity to tilt its sensor and observe a location away from its nadir. That is possible, but changing the swath, increasing the spatial resolution on the go or may not be possible, but in radar it is possible. So, this is one advantage of radar image acquisition. Satellites has this multiple imaging modes which can produce images based on our own needs. And finally, before we conclude this topic, I wanted to just introduce you to the topic of radar interferometry. Where radar interferometry is, radar is not only used for imaging purposes, but by looking at the terrain from 2 different positions in the space, like here this is like a ground point, this is point 1 from which image is taken of the same ground point, this is point 2 from which again the same ground point is imaged. Looking at this or imaging the same ground point from different position in the space will help us to calculate the elevation of this particular point with respect to a given datum. So, using radar images for calculating the elevation of different points on the earth's surface to produce what is known as a DEM, digital elevation model. So, this particular technology is known as radar interferometry. So, here we use the phase information from the radar. Radar not only stores power, it also stores the phase information, we have seen it. Using this phase information, we can collect elevation information about the terrain features. In fact, like SRTM, the Shuttle Radar Topographic Mission, like we know about the space shuttle, right. United States had like multiple space shuttle missions to the space. There in one of such missions they attached radar antenna in the underbelly of the space shuttle. It had like 2 antenna, one in the cargo bay and one like at a certain distance away from the cargo bay, I think some 60 meters or so distance. So, it is like 2 antennas are fixed, one will transmit microwave, another will be receiving the microwave. Okay. So, that is transmit and receive one antenna, another antenna is like just like a passive, it will be just receiving this reflected signal. So, using this phase information between these 2 radar images, people mapped the elevation of almost the entire globe, giving rise to like a radar based DEM. So, this is an example of one of the applications of radar remote sensing. So, not only imaging, but also like we can map the terrain using this radar interferometry. The radar interferometry can happen either in like a single pass interferometry, like we need to acquire 2 images, like image from 2 different positions in space of the same ground point. If it happens in one shot, like as I said before, 2 radar antennas attached at a certain distance from each other. So, there is like a distance between them, they will produce different view angles to the same ground point giving rise to single pass interferometry. The information needed is collected in only one go, whereas if the two images required are collected over two different passes of satellites, we call it as like a repeat pass interferometry. That is also possible. So, in general, collecting elevation information using multiple observation of the same ground point is known as interferometry, and it is one of the most widely used applications of radar remote sensing. So, in this particular lecture we discussed about some important characteristics of terrain surface features which may influence radar backscattering coefficient. Especially we discussed about like vegetation, the moisture content, how it will affect the penetration capacity of the microwave signals, how it will change the polarization and all those things. So, with this we end this lecture, and also we end the topic of active microwave remote sensing. Thank you very much.